Okay, good morning. We're going to continue and hopefully finish the X-foil topic today. I've posted the links for X-foil on Moodle, and I've also just now posted homework too, so you can get started on that. Anyway, so we are on lecture 14 today. So we'll continue with the X-foil demo. So what we are going to do now is we are going to run a sequence of angles using viscous analysis. Of some airfoil, let's say NACA 23015. I'll just pick a Reynolds number of 3 million from alpha equals 0 degrees to 10 degrees in steps of 0.5. This is just as an illustration. Okay, so I'm going to start X-foil and generate the NACA airfoil. Did I say 23015? And I usually just by default use 200 panels. I'd like everybody to do that just so that within the class we are consistent. So PPAR N200, then you hit enter again. And you see that you have 200 panels here. It says so in this place also. Then you do oper, which is operating points, and it will start off in inviscid mode. You can go to viscous mode by typing visc, and it will ask you for Reynolds number. I'll put 3E6, which is 3 million. Mach number is 0. We can put some Mach number. Let's put Mach number of 0.1. Okay, so now when you want to do a sequence of angles of attack, it's always a good idea to run one angle of attack, a good angle of attack within quotes, a condition at which this airfoil will converge, X-foil will converge easily. So usually 0 degrees is good for that. So I'm going to just try to run angle of attack of 0, and we can see that it converged. So now if I want to run a sequence of angles of attack, I can do a sequence, AACQ, go from 0 to 10 degrees in steps of 0.5. And it's pretty fast. It runs and you can see it's converged all of them. Now if you want to run another sequence of angles of attack, you want to continue and do a lower range. So let's say then second sequence from -5 degrees to 0 degrees in steps of 0.5. So usually -5 is a difficult angle of attack. It's probably close to negative stall. It's going to have problems. So a better way to do this is to go from 0 to -5. But then we've gone from 0 to 10, right? If you want to come back to 0, you should really initialize the boundary layer. So using VPAR and then init. So that's what I'm going to do now. So I can do VPAR INIT and then hit enter to come back and do. It's just on the safe side. To be on the safe side, you can do angle of attack of 0. It's converged, and then you do a sequence from 0 to -5 in steps of -0.5. And in this case, it converged. Oh, somebody should have just pointed out. Okay. Basically, I did VPAR init, so initialize the boundary layer. Then I ran again for angle of attack of 0. Then I did a sequence 0 to -5 in steps of -0.5. So, I mean, this is all pretty fast, and you can see all these values are here. What we would like is to have all this recorded on file, right? To write an output file where everything is recorded. That way we can plot it later on. So the way to do that is to use PACC. So there is a command called PACC. So this is called polar data. So alpha, CL, CD, CM, transition location. This list is called polar data in an output file. Use PACC. Okay, so but you should really use the PACC before you run a sequence. So before, you should first do PACC and then you run all the cases, and everything that converges during all of those runs will get recorded onto the output file. So we didn't do that. So all the things that we have got on screen will not get written to file. So let's just, I mean, it takes only a few seconds. So let's just do it all over again. So let me initialize the boundary layer, VPAR, INIT. Okay, now I'm going to do PACC. When you do PACC, it will ask for polar save file name. Basically, what is the output file to which you want to save the polar data? And I try to give descriptive file names. So you can give, file1.out or something like that. After some time, you'll have hundreds of these files and you won't know what is what unless you keep some spreadsheet or something saying file 1 is NACA 23015 at this Reynolds number, this Mach number, blah, blah, blah. But, this is my habit. I try to give descriptive file names. So I'm going to call this N23015 underscore RE3M underscore M point one Mach. Let's just call it 0-1 or something. .pol. Okay, so this just tells me, when I look at the file name, it will tell me, oh, this is NACA 23015 at Reynolds number 3 million, Mach number 0.1. And then save file, dump, it will also ask for a dump file name, and dump file name will have very extensive data on all the boundary layer characteristics for every angle of attack. And that's usually a fairly big file. It's a binary file. You can't open it in Notepad and read it. You'll have to use a special software called pxplot, which comes with Xfoil. But normally Xfoil is so fast that if you want some boundary layer data, you can just open Xfoil, run that case, and go look at the boundary layer rather than generate these dump files. So if you're going to run hundreds of cases, these dump files will soon add up and they'll be taking up disk space. So normally I don't save these. So I'm just going to hit enter, return for no file, right? So I'm going to hit return. So it says dump file will not be written, which is fine. Now whatever I run will get saved into this file. So let's see how that works. Let's run angle of attack 0. Now run a sequence. First alpha is 0, last alpha is 10, alpha increment is 0.5. Okay, this is done. Now I want to go from 0 to -5, so I'll do VPAR INIT, which will initialize the boundary layer, and I'll do alpha 0, and then I'll do a sequence from 0 to -5 to -0.5 degrees. Now it will do all this. Now this is all saved to file, so we can actually quit Xfoil and go here and look, and there is a file called n23015 something something .pol. That's the one I wrote. Let me see if there's some WordPad or something on this computer. Oh, there it is. So this is how the file looks. So the file actually is, so lots of nice things to be learned from the way Xfoil works. So the header tells you that this is an Xfoil output and it's Xfoil version 6.99, right? When you're writing serious code, there will always be newer versions as you debug the code and you improve the theory, right? So it's always good to know what the results are from. It's from 6.99. It tells you the airfoil name and it tells you these things. We'll talk about this later. It says that this has been run for a fixed Reynolds number and fixed Mach number, and the Mach number is 0.1, Reynolds number is 3 million, Ncrit, which we'll talk about later, is 9. Actually, we talked about this, right? Ncrit is the critical amplification factor, which is 9. And it also says that there is no fixed transition. So there is a way to specify fixed transition in Xfoil. And right now that transition is fixed at the trailing edge, which means essentially there is no fixed transition. And here is the sequence of alphas. So first we ran 0 degrees, then we ran 0 to 10. So 0 got repeated again, which is not a problem in the plotting, it's fine. Then we ran 0 again, and then we ran 0 to -5. And because everything converged, it wrote these values here. So if some angle of attack, let's say -5 did not converge, then it would not write this here. So that way you can be confident that anything that's there in the file is actually a converged result. And then there are all these, so this is alpha, this is lift coefficient, drag coefficient, pressure drag coefficient, pitching moment coefficient, and upper surface and lower surface transition locations. Okay, so now you can use this in MATLAB or anything else, but there's a nice associated code with Xfoil called pplot. So if I go to this directory, I see this thing called pplot.exe. And that can be used to plot the polars in a very user-friendly way in Xfoil. So pplot, I'm going to just say pplot, and then it gives me all these options. And first thing I want to do is read polars. So you can compare multiple airfoils or one airfoil at multiple Reynolds numbers, and you can do all that sort of thing. So I want to read polar, and my first polar is N23015 underscore RE3M underscore M0-1.pol. And if you had more polars, you could choose more polars and it will co-plot them. Right now we have only one. And so this is how the polar looks. I'm not sure if you're able to see this very clearly. So we'll spend some more time on what these things mean, but this is the CL on the vertical axis versus CD. So actually the vertical CL axis carries over in all these three plots. So here the horizontal axis is CD times 10 to the power 4. So this value 80 is actually, the CD is 80 times 10 to the power minus 4, because what is listed here is CD times 10 to the power 4. And then this is alpha, so you can see this is alpha, minus 5 to 10. And then this is the transition location. This is the upper surface curve and this is the lower surface curve. No, the other way around. This is the upper surface curve and this is the lower surface curve. So we'll spend a little more time talking about it. And on top it tells you what the airfoil is. And you have a lot of control over changing these axes, limits, and also the other thing that is plotted here is the pitching moment coefficient about the quarter chord. And you can, this is a pretty, well, so you know, pitching moment should really be close to a constant about the quarter chord, and it is. In this region it is somewhat constant. As it comes close to stall, things happen, and then in the negative angle of attack region also some deviation occurs, but at least in this region it's constant. So viscous effects are going to change pitching moment behavior noticeably in some airfoils, in some other airfoils maybe not as much. Okay, so that's what we did, right? So we have run an airfoil in viscous mode, we have plotted it. So it asks for two input file names. One is the polar file. In our case, we gave n23015.re3m.m0-1.pol. I mean, that's just a name I gave. You can give anything you want. You don't even have to call it .pol. I just, over time, I've developed this habit of calling my polar files .pol, because when I look at it in the folder, I'll know what it is. And then dump file. This is a large binary file if you ever write it. I usually avoid writing this file. To save disk space. So this can be plotted using a software called pxplot, which comes with xfoil. Just like pplot is something we looked at, pxplot is another one. Right now I'm not going to look at this. So this binary file has boundary layer data at every angle of attack. So it's a fairly large file. And then use pplot for plotting polar files. Okay. So any questions so far? This is all pretty straightforward stuff. If I went through things fast, it's only because you can. It's only when you start using it you'll start getting familiar with these commands. Okay, I want to talk about how to make this streamlined. So we can always go to Xfoil and we can type one command after another. And I've mentioned before that if you have to do large number of cases, that quickly gets very exhausting. Plus you have no record really of what all commands you typed. So there is a way to avoid that by creating what is called a script file or a run file. So it's just basically it's kind of like a macro. So you know how we open Xfoil and we type one command after another. You can type all of those commands, including the enter keys, right? If you put a space, that's an enter key. You can type all of those inside a file, and then you can pipe it into Xfoil, and Xfoil will just go through all of those commands as if you're doing it one after another. And that's, it saves a lot of time. And the nice thing is, if you run 3 million, and let's say you need to run 1 million, you could just go to that file and change the 3 to 1 and run it through Xfoil, and it'll just go through the whole procedure, and you don't have to really go one command after another. So let's go through that. And I think I've given some example files like that in Moodle, right? Okay, so the other thing we should do, so that this is going to be the focus of our demo. The other thing is, let's, for this, let's use the NLF 10215 airfoil from the UIUC data site. So UIUC has got a big compilation of airfoil data, and we're going to get the coordinates from there and run this airfoil. And that, I think, will illustrate some things you have to do when you get a coordinate file from the internet. So I'll open the browser and go to UIUC airfoil database. Then we'll go to airfoil N, and we want NLF 0215. So that's here. So this airfoil looks like this. This is a NASA Langley designed airfoil. And the coordinates are here, NLF0215.dat. So let's download this. Save as. Okay, so I've downloaded it. Okay, this thing is opening up in Notepad. Let me see if I can open with WordPad, okay. So here's the problem. So this is an airfoil data coordinate list where they've given upper surface from leading edge to trailing edge from 0 to 1, and then where they've given lower surface from 0 to 1. So remember, I was talking about how you have to, for X-foil, you have to go from trailing edge around the airfoil to the trailing edge, right? So what you have to do is you have to actually flip this lower surface, flip the upper surface so that the upper surface goes from 1 to 0 and then continue on to the lower surface. So that's going to be a problem. I usually use Emacs where there is a command to, flip it. So maybe if MATLAB is there, I might be able to do that. Yeah, I mean, I know how to do it in MATLAB, but then right now, I don't know if it may not be here. MATLAB may not be here. Yeah, I don't think they have MATLAB here.
Pretty easy in Excel.
Yeah, if you know how to do it in Excel, maybe I'll use your help. Oh, okay. Wow, it's taking a long time. Do they have Emacs here by any chance? Oh, there might be Emacs. No. It just went to Bing. Okay. Oh gosh, finally. All right, so I'm going to copy this. There are probably better ways to do it, but for now, I mean, maybe you should write a little script or function or something in future if you have to do this routinely. But for now, I'm going to do this. I'm just going to call it I'll just call it xy. xy equals okay. So I've got in this variable called xy, I've got the upper surface coordinates, and I want to flip it. So there's a command called flip ud, and we'll call this xy flip. xy flip equals flip ud, and now it's gone from 1 to 0. I would like to write it to the same precision at least as this, and I mean, I can always do format long. And if I say xy flip, it'll write it to lots of decimal places. For now, I don't care. Okay, maybe if you use sprintf or something, you can write a formatted output. But for now, this is good. So I'll copy this and put it back into Notepad, and then we'll have our coordinate file. Control C, go here. So I pasted this, and I need to remove the upper surface from here. Make sure that there are no spaces, and I don't want these things, so I'll remove these. So the first line can be the airfoil name. I mean, just let's keep it short. So we'll call it NLF 10215F. And then, so now we have upper surface from 1 to 0, lower surface from 0 to 1, and that's it. That's our coordinate list. Are we all set? Can we go to Xfoil now? So remember, you have to remove 0. So what happens now is you have a 0, 0 at the end of the upper surface and a 0, 0 at the start of the lower surface. That will cause problems. That will almost definitely cause problems. So you don't have repeating points in, consecutively. That will break the spline. So now we can save this, and then just to test it, let's go run xfoil, and then I have to load an airfoil, LOAD, load, and what did we call that? NLF0215F.dat. I think it might have saved in the wrong place. So let's save as, could it be, sometimes Windows will save it as a .txt after the .dat, so maybe that's what's happened. It did. So if I do dir, wait, where are we? Oh, we are, no. So let's do right click and look at properties. How do I change it to, yeah, I can go here and say quit. If I do dir here, yeah, that's what, it's called it an NLF0215F.dat.txt. Windows is always super helpful. It thinks you need a .txt and it'll put it without telling you anything. So I can do move, no, ren, I could, REN, in ren is like rename, NLF to NLF. So I'm going to remove the .txt. So now it's the same file. Now we should be good. Let's try it out again. Load NLF0215F.dat. Okay, it loaded. You can see that there is a very sparse distribution of panels. That's because there are only 61 points. So we can do ppar N200 and much better definition of panels. Let's run 0 degrees angle of attack in inviscid mode just to see how it looks. So it's working. So suppose you want to run this at 3 million, you would normally have to put command after command in the xfoil window, and let's say we want to avoid that. So we can create a script file in which we copy all those commands, and the first time you do that, you can go into xfoil, and as you're typing a command, you can put that command into the file. So let's do something like that. So I'm going to create a new file with WordPad, new, and we'll call this save as NLF0215 underscore RE3M dot RUN. I mean, I tend to call my script files or run files as .RUN. You can call it .scr or something. This is just my naming convention. And I want to save this in downloads xfoil. And I hope it doesn't make it a .txt. I think it will, but let's see. Anyway, save. Yes. Gosh, it puts a .txt. Anyway, let the .txt be there. We'll deal with it later. Okay, so I'm going to put this window in a parallel place, or open this simultaneously with xfoil. So what we do in xfoil is we say xfoil, and then first thing we say is load, and then nlf0215f.dat, right? That's exactly what you have to do here also. You have to say load nlf0215f.dat. Just looks weird here. It's putting all these spaces. Anyway, I think it's a simple text file, so it should work. Let's see. Now we do ppar and then n, then 200. Then we give a blank thing after that, right? To come back, we give two blanks. So we have to do the same thing here. ppar n 200, two blanks, and then we are back in the main menu, and then we say upper, and then whisk, and let's say Reynolds number 3 million, 3E6. So upper whisk 3E6. So upper whisk 3E6. Now we do alpha 0, right? And it's converged. So we do alpha 0. Now let's do PACC. We'll create a polar file, PACC, and I'm going to call this NLF0215 underscore, what did I call it before? .re3m.pol. And then I hit an enter to get out of the dump file. So I'll do the same thing here. PACC NLF0215.re3m.pol. Now I'll do an A sequence. First alpha is 0. Let's say last alpha is 20 degrees in steps of 0.5. So that's what I have to do here. A sequence 0, 20, 0.5. And then we have to do a VPAR init to go to the negative angles of attack, and then hit enter. So VPAR init, enter. Now we'll do alpha 0. Now we'll do A sequence for negative angles of attack. A sequence 0 to -5 in steps of, let's go minus 0.25. A sequence 0 to -5 in steps of minus 0.25. And that's it. So at this time everything would have got written, and we go enter to go to the main menu, and then we say quit. So we have to do the same thing here. Enter and quit. And this will save. Oh, this text format is bothering me. It will put a .txt and do weird things. What will happen if I say no? Anybody know about this? Well, we'll save it and see. Yes. Yes. So if I do dir, I see that there is a file here called run.txt. I'm going to rename it to NLF0215. I'm going to remove the .txt just because it kind of bugs me. And then let's show it on screen here in the DOS window. And I think you can say type NLF0215.re underscore re3m. Okay, those are the commands in the file. It looks fine. It's just that in WordPad it seems to put spaces in between and does weird things. In fact, you can open it up in the MATLAB editor if that's more comfortable to you. Now, if we did everything correctly, we'll actually be able to run this with just one command. But before we do that, let's remove the polar file. So delete N23015, no, NLF, I'll delete the NLF polar file which we created when we ran xfoil by hand, right? I want to do it automatically now. So I'm going to delete it, and then now this is where it's really cool. So we created all this run file. Now we can just, with one command, you say xfoil less than NLF 23015 underscore re3m dot run. So less than means everything inside this will get sent to xfoil as a list of commands, and xfoil will behave as if you're typing it one after another. So assuming we did everything correctly. So let's see if that works. That's it. Now it's finished running. And now you can open up the polar file. Yeah, let's go here and open the polar file. So there should be a polar file called, okay, nlf0215.re3m.pol. So there it is. So nlf0215f is the airfoil name. Reference number is 3 million. We just ran Mach number of 0, but you can do whatever you want. And it's got all this data. Now, if you want to now run 0.3 million, right? So let's say, just for curiosity, we'll compare this airfoil 3 million versus 0.3 million. So all you have to do now is go to this run file that you created, right? And then save it as some other name. Save it as 0.3 million is 300K. So I'm going to call it nlf0215 underscore re300k dot run. Right? I tend to save all my script files because 6 months later, if something doesn't look right and I want to go back and understand what I did, I have the whole list of commands. I know exactly what I did, which is, very useful in research, because often you'll want to go back and see what you did sometime back. So I've saved this, and I'm going to save it in text only mode. And all I have to do now is go and change the Reynolds number to 0.3 million. 0.3 times 10 to the power 6. And I have to change the polar file, and we'll call it re300k.pol. And I'll save this, and it'll complain. And then I think it put a .txt being very helpful, so we'll rename it. I mean, you don't have to rename it, it's just, so I renamed it, and now I'm going to say xfoil less than nlf Okay, so if I do this, that's it. Now it will go and do 0.3 million, and it's written the files. Now we can do polar plot, and we can compare those two airfoils. So if you do dir, there are going to be two polar files, one for 3 million and one for 0.3 million, which is 300k. So now let's do pplot. And so even the pplot, you can create a bunch of commands for automating pplot. If there are times when that will be super useful too. But right now we are not going to do that. We'll just do pplot, and I want to read the polars. First polar I want to read is nlf0215 dot re3, what is that file name called? .re3m.pol. And then the next file is nls0215.re300k.pol. Now it's got these plots. So it says the red color is the 3 million and the yellow color is the 0.3 million. This scale is really bad, so you can go change the scale. So I think plot settings is option number 5 is plot settings, and you can change plot inside plot settings. Option number 2 is CD settings, and then you can say what is the CD min, CD max. I usually put 0 to 0.03, which is 0.03 in steps of 0.005. That'll scale the CD axis to something that's useful. Okay, if you do that and then you hit enter again and you say number 3, which is plot CD as a function of CL, it'll replot it, and that's how this plot looks. So you can see how the 3 million, so this is CD, right? So this 3 million has got a much lower drag than the 0.3 million. And also the 0.3 million, this airfoil is really meant for high Reynolds numbers. I purposely ran it at a very low Reynolds number. It's like taking an airfoil meant for a 4-seater big airplane and putting it on a small radio control airplane. It's not meant for that at all. So you can see the CL max is poor. This place has probably got a lot of laminar separation bubbles. But basically it shows you how the performance changes so much when you change the Reynolds number. Okay. So that was just a demo of how you can automate some things. In fact, if you go and you can write a batch file. So let's say you create 100 of these script files, right? You can create a DOS batch file in which you can say xfoil less than this file name, and you can put 100 of those, and you can string together a bunch of scripts and start that and go for lunch and come back, and it would have run all these 100 cases. So we can talk about that if there's interest, but right now I'll move on. Any questions? Yes.
So we wanted to see these plots.
Yeah, that's a good point. So that's what you need for the homeworks, right? So this is purposely designed to have a black background so that it's easy to see on screen. I don't know what will happen if you, yeah, it doesn't. So it's for screen visibility that this is black. I think I talked about how you can get a color postscript or a black and white postscript, right? Did I talk about that? Or
I think so.
So you can create a postscript file. So while you're here, option number 4 is hard copy current plot, right? If you say 4, it'll write this plot to a postscript file, plot.ps, and I think it would have already written it. So there's a plot.ps here, which PostScript used to be a very common format like 15 years back. That's when xfoil was written. Even now, Adobe Acrobat, you might need the full version. It'll convert PostScript to PDF. And that's what it's done, I believe. Yeah, it's just converted it. But if you don't have Adobe Acrobat full version, download something called Ghost View. Ghost View will open up PostScript files. It's a free software. What? So where did it put it? Okay. I think it didn't do it. Something went wrong.
Do you have any issue with us plotting this in MATLAB?
Yes, I would not like you to plot it in MATLAB because your MATLAB files will not have this kind of data.
Okay.
And if you just show me these things, I will not know whether you've run it correctly or not. And it's happened all the time. So I know it's a little bit of a bother to now go and deal with this new thing called a PostScript, which is actually an old thing. It's new for you, right? You've not done it, maybe. I think very few software these days use PostScript. But all you have to do is get Ghost View, and it'll work.
It had a little compatibility issue, so I'm just trying to get through it.
So do you with Ghost View?
Yeah, I think it's just my computer and
Oh, okay.
update stuff, but I don't have it working yet, that's why
Yeah, so it might take a little bit of effort to get it working, but I would rather have this plot than have you do some other plot in some other format, and then I have to struggle with each student to understand what that plot is, right? This is a very standard format, and it's good. So for some reason it didn't. Okay, this file is being used by, oh, I think you know what, I haven't closed pplot, so I think I need to close pplot, and then it'll actually finish writing the PostScript. That might be one problem. Now if I double click, yeah, now it's created the PDF file, and now I can open PDF, the plot.pdf. Maybe. Okay, this is how it looks. So you can rotate it, can't you? What is this? No, this is refresh. View, no. I mean, I guess if I open it in Adobe Acrobat, I can rotate it, but let's try that. Open with Adobe Acrobat. And then view. Okay, so this is how. Oh gosh. I just want to get on with life and not answer questions. Okay, so this is the page. Now, this is what I meant. Did you all read my document that I gave at the beginning of the semester saying general instructions, blah, blah, blah? And so now if you screen capture this, or you can copy as an image or something, like if you can go here and say, copy, take a snapshot or something, then you paste it in Word, this line will become pretty invisible. And so it's a pain. I mean, I'll have to really see what's going on. It's not good at all. But it turns out Xfoil not only changes line color, but also line type. So for most cases, it is sufficient to have a black and white plot. It's actually better. It's so much more visible. So to do that, you can say pplot, and I think it's number 5, change plot settings, and there is a toggle color hard copy, number 13, right? If you say number 13, it'll say switching to black and white hard copy. And then you can, the other thing you can also do is you can write these settings to defaults file. So if you do number 15, wait, before we do number 16, let's do number 2, change CD scaling. And we want to make it 0 to 0.003, right? 1, 2, 3, 4, 03, okay, 0.03 to 0.005. So that's my CD scale. Once you get this right, you can save those settings to defaults file, which is number 15. And usually it's called pplot.def. It's like a defaults for pplot. You hit enter. Next time you open pplot, it'll go and read the defaults. So it'll automatically put the correct CD scale that you like. It'll put the black and white hard copy. It'll do all those things. So it's not as, it's not cumbersome. Now let me read the polars. Gosh, I got to go through all this again. nlf0215.re3m.pol. So this is my plot. And now if I say create hard copy current plot, which is number 4. Before that, let me go and delete the old one. And I'll delete this thing from the PDF as well. Okay, I've deleted them. Now I can say hard copy current plot, and it'll write it to PostScript file, and then 0 is quit. Then now I can, it's only after you quit pplot should you go and convert this plot.ps to PDF. So double click, Acrobat converts it, and now I can open this. And it'll open with the wrong software. I thought I told it to open with Acrobat. Oh, it's trying to do some, I don't know.
Just click on the edit.
Okay, so here is you can see this is actually much better for visibility than a color PostScript. So now you can just go and say, copy file to clipboard or something like that. Oh, I think I have to draw a box. So if I do this box, I think it's copied it. And if you have Word, okay, let's try pasting it. Well, you can rotate it and do all that stuff. There are maybe better ways of copying it, but you can also export it as, you can export to Microsoft Word and do stuff like that. The point is, I think a black and white hard copy is more readable in most documents. So even when you plot 3 or 4 polar files together, the line types are distinct enough that you can, it's visible. The other good thing about writing a PostScript file rather than, you can always go and do a screen capture of the pplot screen, right? But then it will be black background, and so in the Word document there will be one big black background with some lines that are not visible, and then every time you print it, it's just going to eat up all the toner. All right. Any other questions?
Is there any significance to it having lines that carry?
Yes, that is acceptable. I don't know what to do about it. That's how Xfoil is. So, some people, what I would do probably in this case is I would make the CL scale go to 2. So that at least this won't happen. It won't go to the top, right? You will be able to contain it vertically into the axes. The drag is, normally you make plots so that the entire line fits into the axis, but then you can see if you go to high angles of attack, this line keeps going all the way here. If you try to contain all that, the most important part is this part. That will get squished into a tiny region and you won't even be able to distinguish between the 2 airfoils or the 2 plots. So for CD, I would, and I think you will too, it's much better to have this scale and let this run over into the adjacent plots. Very quickly you learn to ignore that. This is actually not very relevant. It's a very high profile drag. It's beyond stall, so profile drag will be very high. And in these cases for the aircraft, induced drag is what matters. So all you need to know is this is very high profile drag. Exactly what it is, doesn't matter too much. But this place you need to know the details. So it's better to zoom in here and let these lines go over, and that's fine. I mean, I don't know what else to do about it. Xfoil doesn't cut it off. I don't think there's any option to trim this here. Yeah, that makes sense. Any other question? Okay. So we did 2 runs, just to quickly capture what we did. And I've got a few script files on Moodle as examples. So if you want, you can take those script files and just make changes and run them. So if you ever use a script file and something goes wrong, like when you run Xfoil it doesn't, it usually means you made a mistake in the script file. So to debug that, the best thing would be to open up Xfoil and go command after command as you have in the script file, and then you'll say, oh, this is where something went wrong. Usually it will be like you're supposed to give a blank line in some places, and if you don't give the blank line, it will get all messed up. So we did NLF 10215 at 3 million, and we did okay. Let's talk about what these polars mean, or how to read the polar files. So the leftmost plot is the drag polar. And the middle plot, one of the middle plots is CL versus alpha. And the right-hand plot is X transition versus CL. Right, so the common axis in all this is the CL. And so this plot may look like this. This usually it's a good scale is from 0 to 0.03. Now this region is called the drag bucket. Some people call it low drag range. It is the range of lift coefficients at which drag coefficient is small. CL alpha curve may look like this. And this curve is going to go like this, right? So ignore CD line going across page. So I mean this plot will probably look like this, something like this. And so this is just the CL alpha curve. If you run more cases, you might be able to get alpha zero lift. And then you also have pitching moment. So there is another scale for pitching moment, and that will look like this. This is the pitching moment. And then you have X transition plots that will look like this. So this is upper surface and this is lower surface. So upper surface transition always moves from trailing edge to leading edge as you increase lift coefficient, and lower surface transition will move from leading edge to trailing edge as you increase lift coefficient. Okay, so let's talk about the drag bucket. So the reason this is called drag bucket is in the past people used to plot CD versus alpha like this. Even now some people do it. And so it'll look like this, and this region is like a bucket, right? But the modern way approach is like this. It's a lot more useful in aeronautics to plot things against CL rather than alpha. Because if you compare two airfoils, NLF 0215 and say NACA NSCA 23015, two different airfoils, right? There is not much use to comparing how does this airfoil at angle of attack 5 compared to that airfoil at angle of attack 5. That's what this kind of plot will do if you do two airfoils. But the thing is, it doesn't make sense to compare two airfoils at a given angle of attack. The better way to think about it is, how do these airfoils perform at the same lift coefficient? Because in an aircraft, lift coefficient corresponds to velocity. So it's like saying when I'm flying this airplane at 100 knots, if I use this airfoil, what is the CD? And if I use that airfoil, what is the CD? And the angles of attack may be very different, but the lift coefficients will be very close. So that's why it's better to compare with CL. And so you might find one airfoil that's like this, and another airfoil that's kind of like something like this, you know. So this is airfoil B, this is airfoil A. And if, let's say, you're comparing at a certain velocity, flight velocity, so of 150 miles per hour, that will correspond to a certain CL, and you're comparing the CD of the two airfoils at that CL. If you compare it with, so let's say you have another airfoil here, comparing at a given alpha doesn't really mean anything. It's just a data point that's not very useful. So that's why this is a modern way of plotting. So this is called a drag polar. Okay, so drag, the rest of it, you know, lift curve, everybody knows what that means. Let's look at transition curve. And I have a couple of minutes. So transition curve looks like this. So we have X transition and CL here. Let's say CL goes from zero to 2 in this example. X transition will go from 0 to 1, and you might have a curve that looks like this. And this is the upper surface, and the lower surface curve may look like this. And so the way to read this plot is to imagine the airfoil below it. So the airfoil goes from 0 to 1, right? Chord of an airfoil. So let's say this is the airfoil. This means at a lift coefficient of 1, transition on the upper surface is here. So maybe this is 0.5. So transition on the upper surface is here. Transition on the lower surface is here. So this is transition locations on upper surface and lower surface at CL of 1. And so what this says is, at low lift coefficients, you have a lot of laminar flow on the upper surface because the curve is here. And as the lift coefficient increases, the transition moves here, and at high angles of attack, high lift coefficients, transition on the upper surface is somewhere here. So very little laminar flow, a lot of turbulent flow. On the lower surface, it's the opposite. At low lift coefficients, you have very little laminar flow, but quickly around CL of 0.5, laminar flow transition quickly moves back. So CL of 0.5, suddenly laminar flow goes from here to here, and then it goes almost to the trailing edge at high lift coefficients. And this region usually corresponds to the drag bucket. So in the drag bucket, both upper and lower surfaces have lots of laminar flow, and that's why, it's in this CL range, CL from 0.5 to 1. It's just this example. This is not going to be, this will depend on the airfoil. Laminar upper surface has a lot of laminar flow, lower surface has a lot of laminar flow. Okay, we're out of time, so we'll stop here. I think you have everything you need for homework 2, and that's up on Moodle, so go ahead and get started.